I want to describe to you how we deal with conservation of energy, okay? And I want to start by talking about this, the most obvious kind of example. And I brought this example up yesterday. Let's bring it up now. Let's talk about a roller coaster. Not super pretty, but it'll do. You have a homework problem that looks something like this, right? So we're basically doing part of that homework problem right now. And I'm going to shut off that light, go stand in my normal place, and contemplate my future. So, if you've ever been on a traditional roller coaster, this part of the roller coaster is the chain lift. Right, you guys know what I'm talking about? That chain that picks up the last car and pushes all the cars up to the top of the ramp. You know that clickety-clackety noise you hear the whole time? Do you find that unnerving? Because they hope that you will find that unnerving. They hope that that will freak you out. Do you know why you shouldn't be freaked out about it? Do you know what it actually is? It's the safety mechanism that's actually in place to make sure if the chain breaks, which happens, the cars don't go back towards the loading house. So what you're hearing is a piece of metal that's just bouncing inside these rivets. And so if the chain was to break and the car was to go backwards, those things would lock in to one of those rivets, and the train would just stay there. And then they would come up and undo your harness and you would leave. That happens all the time. In fact, Hulk is famous for not being shot fast enough and falling back into the loading area. When a ride does that, it's called a W for whatever reason they call it, when a ride doesn't launch successfully. Now, Hulk doesn't use a chain lift. It used a pneumatic lift kind of system, but it's the same idea. It's still trying to put energy into the system. In fact, I don't know. So the chain lift does work on the cars, and ultimately, and this is the part that's important, it doesn't matter, as we showed yesterday, that the cars travel along this path to get there. We showed that the amount of potential energy was path independent. Do you remember that yesterday? Which means that once we get up to the top here, the amount of gravitational potential energy we have is based on how far the cars have been lifted. And they've been lifted from the ground to here. So we would say the amount of gravitational potential energy they have is mg h minus h naught. And what we're saying in this particular example is that we're establishing, and this part's going to be hard for you to catch on to, but not very hard, I hope. We're establishing that red line, that is h naught. That's the baseline. Once we release the cars, this will be the total amount of energy. However, at different points in the ride, the cars are clearly going to be doing different things. So let's say I have point A, B, and C. The total energy has to be the same. And at the very top, I think we can all agree that almost all of the energy is in gravitational potential, because usually when the cars make it to the top of the lift, they're barely moving. Would you guys agree with that? Very little, if not. In fact, SheiKra flat out stops you. So you have no kinetic energy. Most rides have very little kinetic energy at the top of the lift hill. But then after that, this total amount of energy stays the same unless something takes the energy away. So in all three of these places, the cars have the same amount of energy. And this is path independent, so it doesn't matter how they get there. But at every one of those places, the amount of gravitational potential energy they have and the amount of kinetic energy they have has to sum up to equal the total amount of energy they had at the start. And again, it's path independent. It does not matter how they got from one place to another. All that matters is that the cars maintain the total amount of energy unless something takes the energy away. So, let me show you what a typical question would look like. You lift a 100-kilogram car to the top of the lift hill that is 50 meters tall and release the cars. When the cars are at the top of the loop, which has a 20-meter radius, how fast are they going? Everybody get the dynamics of the question? Want me to say it over again? No, you all good? All right. So we're asking about how fast the cars are going at the top of the loop. Well, first, what kind of energy do they have at the top of the hill? Potential. So we start out with potential energy at the top of the hill. This has to be equal to the amount of energy at point C. Point C is the top of the loop. However, is point C as high as the top of the first lift hill? No. So although I'm going to have gravitational potential energy there, I'm not going to have as much because it's not as high. Fair enough? Now, that means there must be energy somewhere else. And if it's not in potential, the other place it's in is kinetic. How high are the cars when they're at the top of the loop? 40 meters, that's right. If the loop has a radius of 20 and the base of the loop is on the ground, then the height of the loop is 40. So if I want to know, say, how fast are the cars traveling at the top of the loop? Well, it would be mg times 50. That's the height of the cars at the top of the lift hill. And over here, mg times 40. That's the height of the cars at the top of the loop. Plus 1/2 mv squared. Everything good? Follow along a little bit? Now, this is not particularly hard to do, and I will point out something. If all I asked you guys was for how fast the cars are going, do you realize that you didn't need to know that the cars were 100 kilograms? Because there's an m in every term. This is why you're never asked how heavy you are when you get on a roller coaster. They don't care. The roller coaster is going to work whether you're big or small because the mass cancels out. Meaning if you're a bigger mass, you add more energy to the system to move that mass. And that's okay. Now you kind of see what you have to do here, don't you? If I asked for how fast they were going, you'd have to plug in a value for g and solve for the velocity. There's not much work now. In fact, we get 10 times 50 equals 10 times 40 equals 1/2 v squared. Now, I think you guys can do this without my help. Is that reasonable? Like this is just arithmetic, so we can look at a different example now? So I want to look at a different example because I want you to understand that although that part's pretty easy, there are other things. So let me show you something else. Okay. Let me change the color of that. So you're going to ski down the slope. And the slope starts 40 meters above where the chairlifts were. This is only 15 meters above where the chairlifts are. Okay. How fast are you going at point A, and how fast are you going at point B? Can you figure that out for me? This is just you practicing before I bring up something else. I have not snow skied, but my understanding is that the chairlift brings you to the top of the mountain. Is that right? You guys who have snow skied? So the guy starts here and will eventually be here, right? So I'm assuming that since the guy starts at the top of the mountain, something gave them energy to get there. So I think the chairlift did it, right? The chair lifted them up to this point, so they now have potential energy here. And they're going to start from rest here. And they're going to go down the first slope, so they'll make it to here, part A. Well, what kind of energy will they have when they make it to A? Okay, potential, that's reasonable. What else would they likely have? Kinetic, yeah, because I don't think they're as high as they were before. So when I see this problem, I see something similar like we just did, that they'll have mg times 40 as their initial amount of energy, and then at A, they'll have mg times 15 plus 1/2 mv squared as the amount of energy they have there. That seem reasonable? And of course, if we take this all the way to its likely conclusion, this will also equal what they have at B, where they have no gravitational potential energy because they're at the bottom, but they have all kinetic. You guys following along with that? Now, of course, I never told you how deep this hole was here. So if this is what you did, you were making the assumption that this red line represents the reference level. Now, I want to impress upon you something that's important here. And this will be the last thing I talk about before I have to leave. H naught represents the reference level. I put it in this equation because reference is valuable, but it's not necessarily about height. When we talk about H versus H naught, what we're really trying to talk about is where is the object likely to go? Let me refine that. My iPad, which I do not want to fall out my hands now, is, I don't know, about 1.5 meters off the ground. This is a meter. So we'll say 1 meter off the ground, right there. I do not want to drop it. How much energy does it have? Is it mgh, where h is a meter? I say this because at one time, this was downstairs. And I had to bring it up the stairs. I clearly did work lifting it up the stairs. So when I ask how much potential energy this has, should I make it relative to the first floor? Is there any chance me holding it here, the object is in danger of falling to the first floor? No. So the reason I put h minus h naught here, and the reason why I keep talking about something called the reference level, is in any one of these problems, your object's potential energy is really a relative measurement. It's relative to where the object could go. Does that make sense? It's not the absolute amount the object's been lifted. Like right now, it's not like I do any work on the object, moving it from above the floor to above the table. Did I change how much energy it really has? But what I did change, and I'm going to use this word incorrectly, I changed its potential of how far it could fall, right? Suddenly, the potential energy should be made relative to the table, because if it fell, it would only be able to fall to the table and not to the floor. You follow what I'm saying? So like all the items on my desk, would I say they have potential energy just because they're above the first floor? or because they're above the floor, like I don't think there's a chance that that remote control is going to fall off the desk where it is. Does it really have potential energy? So when we use potential energy, it's a relative measurement to indicate what the object could do. So when I talked about the box being perched precariously on the bookshelf yesterday, it could fall. It was precarious. So it would make reasonable sense to measure the potential energy relative to the floor, because that's where it could fall to. In this picture, you'll notice that there's a place that's lower than the end, right? If I wanted to know how fast they were going there, I would probably have to do the problem differently and figure out where that level is and use that as my reference level. Does that make sense? So h minus h naught is a way for you to remember what's your reference level. And as a hint, I would always make your reference level the lowest attainable place in a problem. I would always make your reference level the lowest attainable place in a problem.